So, continuing on with our discussion on atomic and nuclear physics. In this video, we cover the concept of the electron spin and the exclusion principle. Electron spin, or simply spin, is a fundamental characteristic of all particles, not just electrons. And just like, say, the Earth, rotating on its axis as it moves around the sun, the electrons, in the case of atoms, the electrons also spin on their axis as they move around the nucleus. Spin is quantized in the same manner as orbital angular momentum. You have capit you have S, spin S, is equal to square root of small s plus s plus 1 times h bar, and you have the z component of the spin as z is equal to ms h bar. S small s is referred to as the spin quantum number, whereas ms is the spin projection quantum number, and it depends on small s. Ms is negative s plus 1, and so on, up to 0, and then up to positive s minus 1, and then positive s. The small s, the spin quantum number, will depend upon the particle concerned. An electron has only one allowed value for s, and that's 1/2. In this case, electron is considered as a special case. As such, for an electron, s is 1/2. That means there are only two allowed values for ms, negative 1/2 and positive 1/2. Ms is equal to negative s, so negative 1/2, and then negative s plus 1, that's what? Positive 1/2, which is positive s. There's no zero value for ms for the electron. There are only two values for ms, negative 1/2 and positive 1/2 for the electron. The spin magnetic moment of the electron is given by the following equation. Mu is equal to E over me s. This is a vector quantity since spin has direction. For instance, in terms of, say, clockwise, you have clockwise and counterclockwise direction, for instance. Or for example, not necessarily applicable to our electron, but it just illustrates that spin has direction. So spin may be considered as a vector quantity. You have the spin magnetic moment mu. The magnitude of mu is given by mu is equal to E over me magnitude of s, and magnitude of s, you will recall, is s is equal to square root of s times s plus 1 h bar. So we have our equation for the magnitude of the spin magnetic moment. Mu rather is equal to E over me square root of s times s plus 1 times h bar. Applying the the value for s for the electron. Again, electron, there's only value for s, one value for s, 1/2. So applying that to the equation for the spin magnetic moment, there's only one value for the spin magnetic moment for the electron, since there's only one value for s. If we use if we have rather Sz, the z component of the spin, we also have the z component of the spin magnetic moment. You have mu z. Mu z is equal to plus minus E h bar over 2m E. Mu z, therefore, or is also equal to plus minus mu b. Notice, E is constant, electron charge magnitude, h bar is constant, me is constant. So this equation may be replaced by just one constant mu b. So mu z is equal to plus minus mu b. Mu b is referred to as the Bohr Magneton. It's equal to 9.274 times 10 to the negative 24 ampere meter squared. Next, we have the exclusion principle or Pauli's exclusion principle. An electron may be completely specified by 5 quantum numbers that we have covered so far. This is particularly applicable for the hydrogen atom, but we can also apply it to other atoms as well. To other, yep, to electrons of other atoms rather. And the 5 quantum numbers we have covered so far are N, L, M, S, and Ms. So an electron in an atom, or in this case the hydrogen atom, may be identified using using the combination of these quantum numbers. Now, Pauli's exclusion principle states that no two electrons in an atom can have the same value for all 4 quantum numbers N, L, M, Ms. As you will recall, for an electron is just limited to 1/2. So it doesn't matter what electron in the atom you are looking at, S will always be equal to 1/2. But for N, L, M, and Ms, the combination of these quantum numbers, no two electrons in an atom can have the same values for all for all 4 quantum numbers. So we can identify what specific electron by these 4 quantum numbers. N is equal to 1, L is equal to 0, M is equal to 0, Ms is equal to 1/2. That's 1 electron. Another electron is 1, 0, 0, negative 1/2. And then you have N is equal to 2, L is equal to 0, M is equal to 0, Ms is equal to 1/2. That's another electron. 2, 0, 0, negative 1/2. That's another electron. So each one is an electron in this table. No electron will have the same combination of these quantum numbers. So say in a large atom, there's 1 electron, 1, 0, 0, 1/2, and there's only 1 electron with that combination of quantum number. The next electron in the atom will be 1, 0, 0, negative 1/2, and there's only 1 electron with this combination of quantum numbers, and so on. To construct the ground state of a neutral multi-electron atom, imagine starting with the nucleus of charge Ze, that is a nucleus of atomic number Z, and then adding Z electrons one by one, bearing in mind the exclusion principle. So, if say the atom has 3 electrons, so 3 electrons, Z is equal to 3. Add the electrons one by one until you complete the Z, until you complete 3, bearing in mind this exclusion principle. So if Z is equal to 3, you have 3 atoms. The first atom will be 1, 0, 0, 1 half, quantum number combination. And then the next atom will be 1, 0, 0, negative 1 half. And then the next atom will be 2, 0, 0, 1 half. And that will be 3 electrons. So again, if Z is equal to 3, you have 3 electrons. So you have first 1, 0, 0, 1 half. And then 1, 0, 0, negative 1 half. And then 2, 0, 0, 1 half. 3 electrons for our atom of atomic number Ze. Electrons with the same principal quantum number n are said to be in the same shell, and those that have the same value of L are said to occupy the same subshell. So n is the shell, L is the subshell. So n is the shell. So 1, 0, 0, 1 half, 1, 0, 0, negative 1 half, they are in the same shell. Shell of n is equal to 1. Whereas L is the subshell, so L is equal to 0, L is equal to 0, so they belong to the same subshell. An electron in the n is equal to 1 state of a hydrogen atom is denoted as 1s, s being the 1 rather being the subshell, is the shell rather. If n is equal to 2, then the subshell, the denote is 2, say 2s, where the first digit indicates the shell, n is equal to 1, and the letter indicates the subshell. Diba? L is the subshell. So, S, P, D, F corresponds to the letter L. L is equal to 0, 1, 2, 3, and so on. So, L is equal to 0, S. L is equal to 2, P. L is equal to 3, D. L is equal to 0 rather, S. L is equal to 1, P. L is equal to 2, D. L is equal to 3, F, and so on. So sorry about that. 2 electrons in the N1 state are denoted as 1s2, where the superscript then indicates the number of electrons. So if just 1s, 1 electron in the shell, 1s 2 electrons in the shell, and so on. So for example, the combination of 2 electrons in the n is equal to 2 and I is equal to 0 state, and 3 electrons in the n is equal to 2 and L is equal to 1 state is written as 2s2, 2p3. 2, n is equal to 2, L is equal to 0, so S, 2 electrons, so 2. And then 3 electrons in the N2 state, N is equal to 2, so 2. L is equal to 1, P. And then 3 electrons, 3. So 2s2, 2p, 3. This representation of the electron state is called the electron configuration of the atom. So some examples of the electron configuration, you have the hydrogen 1s1, helium 1s2, lithium 1s2, 2s1, you have carbon 1s2, 2s2, and 2p2. Electrons in the outer shell, so in the outer shell, denoted by N, of course, electrons in the outer shell of an atom are called valence electrons. So hydrogen has only one shell, one. The electron in this shell is a valence electron. Whereas carbon has two shells, one, two. The electrons in the two shell, n is equal to 2, are called valence electrons. The maximum number of electrons in a subshell depends on the value of the angular momentum quantum number L. Of course, L is the subshell, or L denotes the subshell, so the maximum number of electrons in a subshell will depend on L. N is equal to 2 times 2L plus 1. So again, number of electrons, maximum number of electrons in a subshell, capital N, is equal to 2 times 2L plus 1. So for instance, say L is equal to 1. So 1 times 2 plus 1 is 3. 3 times 2 is 6. So the maximum number of electrons in the subshell L is equal to 1, or P will be 6, as illustrated in this table. L is equal to 1, so that's P. 1, 2, 3, 4, 5, 6. 6 electrons in the subshell P. And that's it for now. We'll continue our discussion of atomic and nuclear physics in the next video. So thank you for watching.